Hi, in this session I'm going to talk about special relativity. I'll start with how people think about relative motion before the time of Einstein. The method is called Galilean transformation. Now, what it means is this. We think in terms of frame of reference. Now, the term frame of reference basically means from the viewpoint of an observer. So for example, I would have in this frame of reference one observer, and in that frame of reference another observer, and the idea is that one observer would be moving relative to the other. So if, say I imagine that this is me, I'm at rest, and this is another observer this is my friend who is moving maybe in a car at a velocity of v in that direction. Now, Galilean transformation is a set of equations to calculate the coordinates of one from the viewpoint of one observer given the coordinates in terms of the coordinates from the viewpoint of the other observer. And this is what it looks like. So what it means is this. For example, if I look at the origin, now at the origin, from the viewpoint of this observer, who is at rest, the origin will be at x equals to 0. Now at the time t is equal to 0, that origin will be at the same place as this origin. And so when t is equal to 0, x will be 0 and x prime will be 0. So those 2 points will be the same. But as time passes, you see this term here, it becomes more negative. So x prime becomes more negative. And what this means is that from the viewpoint of this moving observer, he thinks that at first the origin of the other observer is at his origin, but as time passes, the origin of this observer moves more and more to his left. So as far as he is concerned, the origin of that observer, which would be the x prime, becomes more and more negative. That's why we have this equation. That's why it looks like this with the minus vt down there. And vt is the distance that this origin has moved to the left of the moving observer. Now, what is even more important is the next equation, which says that t prime is equal to t. So t prime is a time as measured from the viewpoint of the moving observer, and t is a time measured by the stationary observer. And what it's saying is that the 2 times are the same. And that means whether you are moving or not moving, or however fast you're moving, the time that different observers measure are exactly the same. So that's the way people think about relative motion before the time of Einstein. But what this method implies is that, for example, if you have a light coming towards you, if someone shines a torch at you, imagine that we can measure the velocity of the incoming light, we would find a certain velocity. But now if I start running towards the light, then I should find that the light is faster. Okay, because as the light comes towards me and I run towards it, the light should appear to come towards me even faster. So that's the relative motion. So I would expect that the speed of light is different for different frames of reference. And it becomes quite obvious if, for example, if I have a light ray going in this direction, and suppose I can run as fast as the light, then I would expect that I'll be running together with the light, and the light would be at rest relative to myself. So it's obvious, of course, that based on this idea, the speed of light should be different, right, depending on whether you are moving or not. Right. Now, but is that really true? It's difficult to tell because light is so fast. But there is an experiment that has been carried out about 100 years ago to check this in a sense. It's called a Michelson-Morley experiment. Now the idea is that this experiment is an interferometer. So there is a light. There wasn't a laser then. So there's a beam of light, and there is what is called a mirror, that a partially silvered mirror or a beam splitter that can split, allow some light to go through and reflect some light. So we call that a beam splitter, and there is a mirror there and a mirror there, right? Now, and there is a telescope here to observe the light. Now this light would be reflected from that mirror and comes through here. This light reflected from this mirror and reflected from the beam splitter will come through here. So we have the same light split into two, reflected back and coming through to this place where an observer looks. Now when the two lights recombine, they interfere and produce interference fringes. Now the idea is this: the interference fringes depend on the relative distance traveled by the two rays. And if the distance of this path, of either path, changes, you will see the fringes move, because they reconstruct and they interfere constructively or destructively depending on the actual path length, the relative path length. So, and what happens is this: the idea is that this experiment is carried out on Earth, and Earth is moving through space in a certain direction. So if we do this experiment in a certain position on Earth, and then we rotate that experiment so that it moves through space with Earth in a different orientation, then the path length in this direction and in that direction will change. If I rotate this, alright, depending on how it relates to the direction of motion. So therefore, the fringe pattern that we observe here will shift. Now, this experiment would be able to give us an idea of, say, which direction the Earth is moving in space relative to this laboratory. Now, what was very surprising was that when after this experiment was carried out, it was found that the fringe patterns did not shift at all. And what this means is that when you rotate this around, the fringe pattern did not shift, and it seems to show that the speed of light does not depend on the direction of motion of the observer. And this was a null result. That means it's an experiment that gives a result that is nothing, that is zero. Okay, and this suggested something very fundamental. To Einstein, it suggested that the speed of light does not change. That means that if I have a torchlight shining towards me, then even when I'm running towards the torch, I would measure the same speed. Or if I have a torchlight shining past me and I run along with the light, then no matter how fast I run, even if I think I can run as fast as the speed of light, when I measure the speed of light, it will still be the same. It will still be the same speed of light relative to me, meaning that I can never run as fast as the speed of light. So this idea that the speed of light is the same for all frames of reference, meaning to all observers, no matter how they are moving. We call it the invariant of the speed of light, or speed of light invariance. So this becomes the basic postulate for special relativity, and it is from this that we can derive things like length contraction, time dilation, and eventually E equals to mc squared. So let's see how that happens. Now, if the Galilean transformation looks like this. That was a Galilean transformation, and it relates the coordinates x and t in one frame of reference to x prime and t prime in another frame using a set of equations which is linear. Linear just means that the answer is obtained by taking one variable, maybe times some constant, and another variable times some constant, and then just adding them together. So linear in the sense that there's no x squared or x cubed or t squared and so on. So linear in that sense. Now, and the idea is that if we now have this new idea that the speed of light is invariant, that does not depend on the frame of reference, then obviously the Galilean transformation has to be different. So, that means that there must be some new equations. Now, what are these new equations? And the way to get these new equations is to start by making some guesses. So first of all, we will say that, right, in one frame of reference, we would measure, say, that the position of and time of some event is x and t. And then what we hope is that in terms of this x and t, we can then calculate what are the corresponding x prime and t prime from another frame of reference that is moving relative to this. But to find this equation, we start by making a simple assumption. And the simple assumption is that the relation between them, although it's different from Galilean transformation, they are still linear. So, linear means that, as I said, it is x times some constant plus t times some constant, which we don't know, and added together should give you, for example, x prime. Okay? And x times some other constant plus t times some other constant added together should give you t prime. So in that sense, they are linear. So we are making this guess that the relation is still linear, but we don't know the new constants, and we have to find these now. And the idea is this. Let me draw this frame of reference again. R, x prime, that's the origin of x prime and the origin of x. Right, so we start with the understanding that when time t is 0, the two origins coincide. So as time passes, the origin of this R prime frame moves to the right with a velocity v. So as far as this observer is concerned, if he keeps looking at the origin of his moving frame, of this moving frame, then he'll see that the origin moves to the right with this velocity v. And because it started at his origin, he would think that the coordinate of that origin is x in his own coordinate equals to v times t his own time. Alright, and this is when he is focusing on this origin where x prime is 0. Okay, so that's the understanding. And we can substitute these values here into that first equation. So let's see, x prime is 0, x is vt, and we still have vt. And if we rearrange this, I can solve for b. The t and the t cancels. Alright, and I have minus gamma v is equal to b. Now, if I substitute this back into the first equation, I'll get x prime equals to gamma x minus gamma v t. Right, and I can factor out the gamma x minus vt. So this is what I have. Okay, now let's do a little bit more. Now let's think about the speed of light. I have this relation. Now if I have a speed of light, say traveling out from this origin, alright, say starting from t is equal to 0, I have a light going out in this direction, and it goes out, it would go out at the speed of c. Now at the origin, at time t equal to 0, both these origins coincide. Alright, and then I switch on the light and the light starts moving in that direction. So from the viewpoint of this observer, I would have a relation for the position of the light as it moves. And that would be x is equal to v is equal to c times time. Alright, likewise, from the point of view of that observer, I would have x prime is equal to c times t prime, would be the position of the light as it moves. So what I'm going to do here is that I'm going to substitute the t from here in terms of x into the t in this equation. Right? Let's clear this off. So that means t will be equal to x over c. So if I make that substitution, I'll get x prime is equal to gamma x minus v, and t would be x over c. Right, that's what we have. And since x is a common factor, let me factor it out. I get gamma of 1 minus v over c times x, that's x prime. So, okay, all I've done is I've made a substitution. Right, and so far we have been looking at this from the viewpoint of this observer. Alright, now that other observer is moving to the right relative to this one. Now let's look at this from the viewpoint of that other observer. Now from that viewpoint of that other observer, he would also think that the speed of light is the same. Alright, even though he's moving along with the speed of light, we are going to insist on this assumption or postulate that the speed of light is the same no matter how you're moving. So because of that, as far as he is concerned, that speed of light started off from his origin. Okay, at the time of the start, those two are at the same place, and it moves to the right at the speed of light, and therefore he would also agree with this equation where the position of the light is equal to the speed of light times the time. So he would agree that it goes at the same. He would observe that the light goes at the same speed, and now, so what we could do is that we could repeat the previous steps, alright, and obtain a corresponding equation to this one. Now, rather than actually repeating the previous step, what we see is that we make use of the understanding that the equation from the viewpoint of this other observer, they should have the same form, right? In other words, they should have the same format as this. And all you really need to do is, if you want to switch to the viewpoint of that other observer, you will just exchange the coordinates. So replace x and t by x prime and t prime, and replace x prime by x, and replace the v by minus v, because v was the velocity of one relative to the other, and if you go to the frame of the other observer, then as far as this other observer is concerned, this frame would be moving to the left, and so the v should become negative. So in order to switch from one frame to the other, we change the unprimed coordinates to prime, and we change the primed coordinates to unprimed coordinates, and we switch the sign of the v. So that's all I need to do in order to switch frame of reference. So this is what it will look like. Now, so minus v become plus v. X there become x prime, and x prime there becomes x. Alright? So now I have these two equations. Now the point of doing this is to solve for the unknown constants. Alright, remember we have this new set of linear equations, but the constants are not known yet. And the constant in this case would be, we have gamma there, which is the constant we want to find. So to solve for this constant, right, let's make use of these two equations. We have these two equations now. What we could do is we could multiply those two equations. Now if I multiply these two, I get x prime x. Multiply the gamma, I get gamma squared. Now if I multiply 1 minus v over c by 1 plus v over c, okay, when I expand that, I'll get 1 minus v squared over c squared. And then I have x times x prime. Now this is convenient because I have x prime x and x prime x on both sides. And I can cancel them. So I have just this. And now I just have gamma squared as the unknown, and I can solve for it. So gamma becomes equal to 1 over, bring this over to the other side and take the square root. We have the familiar Lorentz factor. So we have one expression here for gamma. Now if we look back at this first equation there for x prime, you see that we have solved for gamma. And that means that we have the two constants that we need for that first equation. Okay, let me write that down. So this is my first new equation, x prime equals to, repeat that one there. I'll factor out the gamma. Okay, x minus vt. So that's one equation where I now know that gamma is that Lorentz factor. Now I need the other equation for the time. We can make use of the relation for speed of light again. The idea is to express those two is to notice that the x prime there is equal to c times t prime, the light speed times the time in that frame of reference, and that the time there is equal to, that means the time in this frame is equal to the distance traveled by the light divided by c. Okay. X over c. X prime is ct. And the x there is equal to ct. Right. So to have it in terms of time, I simply make use of the relation between time and the speed of light. So we could now substitute these into there and see what happens. So ct prime is equal to gamma times ct minus vx over c. Now if I divide both sides by c, t prime equals to gamma divided by c, that's x. Okay, and divide that by c. So that's Vx over c squared, and this is c squared. So now I have the equation for t prime. Now I have the other equation. And the unknown constants have appeared automatically once we make this substitution. You see that that's the t, and the unknown constant is the gamma, which multiplies the t, and that's the x, and the unknown constant would be minus of v over c squared times gamma. So we have found all the unknown constants, and these are the two equations, that one and that one. So now we have a set of equations relating the two frames of reference, relating the coordinates there. And this set of equations has a name. It's called Lorentz transformation. As opposed to Galilean transformation, which assumes that the time at different frames is the same and light can have different speed. So now we have a transformation in which the light speed is the same in all frames of reference, however you're moving, whether you're running with the light or towards the light. Now we can now derive length contraction and time dilation. So let's do that. I'll start with the two frames of reference again. Okay, and that's R and that's R prime. So one observer here at rest in this frame, another observer at rest in that frame, and this frame moving velocity v to the right relative to this frame. Now suppose I have a ruler in this frame of reference. That means that this ruler is at rest relative to the observer here. And suppose that the ruler has a length L. Okay. Now this ruler, the two ends of the ruler, suppose that the coordinates are xa prime and xb prime. Okay. So as far as the this observer is concerned, that's what he sees. Now, but for this observer, he will see the ruler moving relative to him, and he will measure a certain values for these two coordinates relative to his origin. Okay, and we know how to calculate these values in terms of the value of this observer. That's just a Lorentz transformation, and it looks like this. Now, this observer, all right, he would think that this end of the ruler is at a certain xa without the prime. Okay, so he would measure this ruler as moving and changing with time. Okay, so we'll let that be xa. And suppose that this observer here, if you like, let's say he takes a picture. This observer who is at rest here has a camera, and he takes a picture of this moving object so that he can measure it at his leisure. And what he'll see is that when he takes his picture, he would be at the same time recording the positions of the two ends of the ruler. Alright, at the same time, say time t. He will record that at this time t, one end of the ruler is at xa in terms of his coordinate, and at the same time t, the other end is at xb in terms of his coordinate. Alright, when he measured from his origin. And in terms of these coordinates, we know that xa prime, the coordinates of this end of the ruler as seen by this observer, is given by this equation from the Lorentz transformation. Likewise, the other end of the ruler, xb prime, is equal to this. Same equation, a similar equation, right? So we have this. So with this relation, we can now find the length measured by this observer. That's what we are interested in. We want to know whether the same ruler, when measured by a moving observer, would be different. So, in order to find that, we can subtract the two. Now, if you subtract this, here you get, I'll subtract the first equation from the second equation. So I have xb prime minus xa on the left, and on the right, right, vt and vt cancels. I'll have xb minus xa with a factor of gamma. So this is the length that is measured by this observer. Alright, with his camera picture, he can measure the positions of the two ends of the ruler and subtract them. So to find the length. Now this length here was the L prime. This is the L prime, and that's the length according to this observer. where the ruler is at rest. So now, if you look at these two, let me solve for the length of the ruler for this observer. I'll move the gamma over to the other side. And that's what we got. So this observer measures the length of the moving ruler, and this is the answer that he got. Alright? The length of the ruler from the viewpoint of the moving observer. Alright? That means in the rest frame. In the frame where the ruler is at rest. Divided by the Lorentz factor. Now, is this longer or shorter? Okay, let's have a look at the Lorentz factor. The Lorentz factor is 1 over this. So it's 1 over square root of 1 minus v squared over c. Now, for now, let's just assume a velocity of v that is not too big, that's less than the speed of light. Now you can see a problem if v is more than the speed of light, you have 1 minus a number that is more than 1. And that does not work. We'll talk about more on that later on. But for now, let's say if you look at this v squared over c squared, it has to be a positive number. Alright, so if you take 1 and minus a positive number, your answer will be less than 1. And if you take 1 and divide by a number that is less than 1, this answer has to be more than 1. That means that gamma must always be more than 1. Now, going back to this equation, we have the length of the ruler divided by a number that is more than 1. So the answer has to be smaller. Alright, so that means that xb minus xa has to be smaller than the length of the ruler. Right, by which I mean the length as in the length in the rest frame of the ruler. So as far as this observer is concerned, he sees that ruler moving, and when he measures the length of the moving ruler, he gets a result that is actually shorter than the length of the ruler. So in this way, we have just predicted length contraction. Right, in the next example, we'll derive time dilation. The idea that the clock, a moving clock, runs slower. Let's see how that happens. Alright, let's start with our two frames of reference. R, X there, origin there, and another frame or observer moving relative to the first one. Okay, so in this moving frame, in this frame of reference, let's say there is a clock. Alright, now let's say it's not a digital clock, it's the old type of clock with hands on it. So at a certain position of the, say, the minute hand, let's say the time here is TA prime. And then after some time, the minute hand moves to another position around there. Let's say it's TV prime. So this observer measures the duration of this time, and it would simply be TD prime minus TA prime, just by looking at the clock. So that's quite straightforward. Okay, and the position of this clock would be at a certain value of x prime. Just call that x prime. Now let's go to this other observer. So this clock is moving there to the right with velocity v. Let's think about that observer. So this observer would be watching this clock go by. Okay? Well, it goes further and further away, but let's just assume that he has cameras there which is at rest with respect to him, which can say take a picture of the clock at different times. So he has his own clock. He or she has his own clock. So using that clock, they will check when the minute hand was here at the start. This observer will check their time, and when the minute hand reaches the other position of the clock, this observer will check their time again. So let's say when the time here, when the minute hand is there at the time ta prime and the position x prime down here, this observer checks their clock and found that their time was ta. Alright? Now when the hand of the clock reaches the other position, this observer measures Tb prime, and the clock is still at x prime, at rest with this observer, same x prime position. But this observer, when they see that the hand of the clock has moved to that position there, looks at their own clock and records Tb as the time. Alright? Think about this experiment. And we know how these coordinates are related. They are related by the Lorentz transformation. Let's write down that relation. Right? The bracket there, a gamma outside, with a v squared v over c squared for this. Now the Lorentz transformation that I've written down just now had a minus sign there, but that related x to x prime, meaning that the coordinates here do not have the primes, the coordinate there has the prime. But now, in this way that I'm writing it, I'm calculating the coordinates of this frame from that frame. So this frame, as far as this observer is concerned, that frame is moving to the left. Alright, so I have to switch the sign of the v, so the minus here becomes a plus. Alright, once we have this form, for Tb it looks similar. And I have the two equations. So once again, I want to compare the duration of the time measured by this observer and by this observer. I could subtract the two equations. Let's do Tb minus Ta. Notice that these two terms are the same, so they cancel, and I have just Tb prime minus Ta prime with the factor of gamma. So now I have the relation between the time duration measured by one observer and the time duration measured by the other observer. So this is measured by an observer which is at rest with the clock, but this is measured by an observer where they see the clock moving. Now from just now, we know that gamma has to be more than 1. So therefore, as far as this observer is concerned, alright, the time measured would be longer than the duration of the time measured by this observer who is at rest with the clock. And that's our time dilation. Alright, it's a time dilation because the clock here appears to run slower than the clock there, according to these results. We'll stop here and continue later with relativistic dynamics.